morning and welcome to this morning's session on the UK's evolving energy mix, achieving net zero carbon and reduced energy costs with Clarke Energy, INEO and Sterling Pharmaceuticals. Hopefully the slides will appear shortly. Perfect. Good morning. Welcome to this session, and I hope you're in for an hour and a half of enjoyment featuring myself, Adam Ray Summerson, Project and Market Development Manager for Clarke Energy, Paul Lunn, Plant Engineer for Sterling Pharmaceuticals, and Michael Smeeth, Global Resiliency Leader for INEO. Excuse me. Initially, I would like to discuss setting the scene almost for the energy landscape and how it's changing within the UK. I'd like to start that, if I may, with a brief introduction into Clarke Energy, a global business that still holds a local family feel. We were established in the late 80s as a small service business operating primarily in those days in the marine and offshore industries. In 1994, we were approached by Yenbacher GmbH, wanting a strong service partner in the UK to help them penetrate the UK landfill market. Since then, we haven't looked back, and we now represent them in 27 countries worldwide with an installed base exceeding 7.2 gigawatts from a range of gaseous fueled power generation applications. That global experience penetrates both natural and non-natural gas applications. We understand local challenges, market drivers and inhibitors around the globe, and have a considerable experience of a range of power generation solutions. Our methodology is fairly simple. We want to be as flexible as possible as an energy solutions provider. That could range from a gas gen set featuring an engine, generator and control panel, right the way through to an engineering procurement construction contract featuring multiple engines arranged throughout multiple fuels, up to and including hybridized solutions that incorporate both energy storage and renewables. Essentially, we have a complex energy system comprising both centralized and decentralized plants at this kind of phase, connected via somewhat arguably constrained transmission and distribution systems. And as more distributed energy solutions and increased levels of intermittent renewables are added to that system, network stability in turn has been affected. Adds to the complexity of maintaining quality in terms of voltage and frequency throughout the network, particularly at peak times. And it's probably going to get worse. You know, global energy demands are increasing, forecast according to the World Energy Outlook to increase to some 40,000 terawatt hours by 2040. So understanding the mix of generation, the cross-border importation and export of electricity, how we achieve that demand needs to be understood. Coupling these growing energy demands, with increased global temperatures and emissions of CO2 since the Industrial Revolution are clearly having an effect on climate, which in turn, arguably, whether you believe scientists or don't, certain global leaders could be contributing to frequency of natural disasters and raising sea levels. The Intergovernmental Panel on Climate Change recommend that significant changes are needed to human activity globally in order to curtail harmful emissions to atmosphere. And those harmful emissions do encompass other things, but you know, carbon is really the focus because of the residual time that CO2, carbon dioxide, remains in atmosphere, as illustrated on the slide here. Concerningly, half of all human-related CO2 emissions have occurred in the last 40 years. which has resulted in atmospheric levels now in excess of 400 parts per million. So clearly there is a problem that growing demand globally is contributing to those increasing levels of CO2. So what are we doing about it? The UK government has made commitments to reducing those emissions with a target to net zero by 2050. Devolved administrations in Wales, Scotland and Northern Ireland are all keen to hit those targets sooner, if possible. So far, as can be seen from the graph here, energy throughout the UK has made that greatest effort to decarbonise, but there's still clearly a way to go. UK policy is starting to reflect now the additional needs that will be required, such as only burning natural gas with carbon capture or accommodating increasing levels of hydrogen within the gas system. But how can we continue to decarbonise our respective energy systems despite this trend in increased demand? Several technological considerations would result in varying levels of emissions reduction. And combinations of all of these technologies kind of illustrated with increased penetration of renewable energy will be paramount. I mean, if we take it a step back and look at kind of the historical core arguments for CHP, arguably there were three kind of considerations, but we were driven primarily by the savings achieved, not only in terms of financial saving, but the avoided imported electricity and the associated transmission and distribution losses, and the effective use of heat generated as a byproduct of that on-site generation. So we're increasing our overall efficiency from the offset. But as the carbon intensity of grid-supplied electricity falls, the emission reduction benefit has become less prevalent in the UK, albeit CHP does and can still provide a net saving in certain applications and will continue to do so into the 2030s. In other countries where there's still a large proportion of carbon-intensive generation on their networks, that emissions reduction benefit is clearly still an important advantage and an important consideration of CHP. Economics clearly continue to be a huge factor, particularly considering the rate at which electricity prices have and continue to tend upwards. Though increasingly, our inquiries suggesting a greater prevalence toward resiliency of a client's operation. What happens if the grid fails for a short period of time or for a longer period of time? How can I ensure the resiliency of my ongoing operation? The Climate Change Committee stated, I think in 2018, that to help meet government carbon reduction plans for 2050, a minimum of 18% of thermal demand throughout the UK should be met by heat networks. Current deployment is probably around 4 or 5%, serving some 14,000 schemes in the United Kingdom. These schemes provide heating and in some instances cooling to around 477,000 final customers, approximately 34 customers per scheme. But future district energy schemes will need to take into consideration a mix of generation technologies and smart management systems, data collection, data interpretation, to operate with the highest efficiency and lowest emissions at all times. Efficiency gains, lower emissions can also be met by migrating our traditional backup generation fleet to flexible fast start gas engines, such as INEO's J620 fast start version. With transient low characteristics comparable now to diesel engines, at higher efficiency and with lower emission, this becomes an interesting proposition to displace aged backup infrastructure as part of modernisation strategies. Equally, as energy storage prices continue to fall, this is becoming a much more viable solution for providing not just backup power, but also peak load cover, and offers the ability to participate in providing grid services such as balancing mechanism or frequency response. In considering modernisation, backup infrastructure, monetization of these assets is also becoming more important. So not just solely having this as a backup opportunity, but also how we can possibly participate in these market activities as well as providing that backup infrastructure. Clearly, we're facing a host of changes as well within our gas composition within our networks, resulting in global changes to that overall composition. For example, increasing methane numbers through increased levels of LNG, liquefied natural gas in the UK gas system, for example. But where gas is considered negatively in an environmental capacity, the reality is that this is still much less polluting than coal or oil. So should we still be considering this as an interim solution on that path to zero? With WOBE index varying from country to country and latest standards permitting a greater level of variability, as well as the potential for introduction of hydrogen gas into the networks, the ability of gas-fueled assets to perform under wider parameters is fundamental, which is why Jenbacher, as we'll hear from Michael later on, are working closely with relevant European bodies to ensure we understand what's coming down the pipe, so to speak. Looking at some of the other technological kind of developments then, with biomethane injection, a process whereby we dry biogas with sulfur removed is compressed before entering a membrane filtering system. It's also an important consideration moving forward. Current UK generation from anaerobic digestion, from waste and farm, is around 429 megawatts electrical, not including landfill generation, wastewater or sewage treatment. Presently, UK biomethane injection is in the region of 50,000 normal meters cubed per hour and growing. Hopefully, the green grass levy consultation could help shape the future of biomethane injection, and we can see more renewable fuel being added to the system, helping us to decarbonise the gas network. Understanding the hydrogen supply chain, and I think critical to unlocking that hydrogen supply chain, will be transitioning from blue hydrogen to green hydrogen. Hydrogen that's produced as a byproduct of certain processes to hydrogen that's produced as a process of renewable generation. And integrating carbon capture where we can utilise naturally occurring formations, such as those vacated through extraction of gas and oil, to avoid that transmission of CO2 to atmosphere is going to be critically important. But part of the conversation really needs to consider the technical viability of carbon capture, utilisation and storage, and the economic impact that this brings. By this, I'm referring really to the links between the point of generation of that carbon through to the point of storage and the infrastructure required to get it there. For example, the St Fergus scheme, up in the northeast of Scotland, we can deduce really that the main reasons for this project moving forward at reasonable cost right now is that existing infrastructure is being utilised in terms of the gas pipe to the geological formation. So is this technology really that will be better suited to supporting heavy industry with fewer, albeit larger individual contributors? Distributed generation, the behind the may need to be more reliant then on carbon-free supplies of fuel, such as biomethane and hydrogen. Thinking about hydrogen and where we get it from, electrolysis, for example, splitting water into hydrogen, 100% efficient electrolyzer requires around 40 kilowatt hours of electricity to produce approximately 1 kilogram of hydrogen. So if we assume an average electricity cost right now of 12 pence per kilowatt hour, it costs approximately £4.80 to currently produce every kilogram of hydrogen. Now, clearly, moving away from dependence on grid supplied electricity and utilising excess renewables helps with that cost factor of generating hydrogen and helps ultimately with the carbon intensity of the hydrogen that's being produced. Other processes, including biochemical processes such as producing syngas or fermentation, to produce that hydrogen directly, or thermochemical processes such as using high temperatures and pressures in the presence of a catalyst to force that chemical reaction, are considerations to be made again in this scale of blue, grey and green hydrogen. Where is hydrogen coming from? Currently, steam methane reformation is probably the most cost-effective means for hydrogen production in the UK. However, it does also produce considerable carbon emissions. So again, carbon capture becomes a very important piece of the equation if we're considering steam methane reformation. Hydrogen production facilities are working hard to produce what is essentially a valuable commodity and a commodity growing in value. But to get to where we need to be to realise the true decarbonisation of the network, it will require significantly more hydrogen than is currently available, circa 27 terawatt hours in 2018, But 2018's natural gas consumption within the UK was some 880 terawatt hours. So clearly there's some way to go before we can get anywhere near the total gas demand of the UK. But there is considerable work ongoing within the industry to ensure that an increased penetration of hydrogen is available. As part of BEI's funding programs to support development of low carbon industries, we've seen a number of low carbon hydrogen clusters beginning to form, supporting the acceleration of that development of the fuel generation and also of the potential impact to equipment connected to that, combustion equipment connected to those clusters. One such scheme, such as HyNet in the Northwest, involves several different businesses working together collaboratively to help develop an integrated hydrogen economy, which is really quite interesting. Some of our current customer base in this area, in this part of the world, are involved with the scheme, and we're very keen to explore with them how increasing and varying levels of blended fuel might impact our existing generating equipment. There are also a few notable schemes throughout Europe at various levels of development, showing one common theme and common drive, that is, to achieve our decarbonisation targets, we all need to work together to understand both supply side and demand. The German concept, for example, which has been presented by German gas grid operators, is to achieve 100% hydrogen grid by 2030. Very ambitious, and we certainly wait with excitement to see how that scheme continues to develop. The proposed changes to international gas standards, as I've said, to policy rhetoric relating to increasing levels of biomethane and potential for hydrogen within the gas system are all great and will help us decarbonise that national gas grid. These changes could have significant implications to engine performance and operation, but should be considered as an opportunity for future-proofing our design through understanding the implications and planning for them. For example, understanding that blends of up to 20% by volume of hydrogen will have minimal impact to both performance and ongoing operation is reassuring. But beyond those levels, modifications to to hardware and software within the engine systems may be required, which could be facilitated during routine maintenance to minimize the impact of operation. So essentially a natural gas investment right now, you can utilize the carbon savings that will continue to make into the 2030s, and more importantly, the financial savings that will make. And then as increased levels of hydrogen come into the network, we can cope with the lower levels. And if we get above 20% by volume, we can make changes to existing assets in the field at times of overhaul. So you're maximizing the savings right now to invest in that true renewables, low carbon, zero carbon future. Our customers are focused on reducing emissions, delivering resilient operations, and where possible, want to continue to save money. Low and zero carbon generation technologies can be expensive, with some still requiring government subsidy to ensure penetration at the required level, if we're truly to make an impact to our decarbonisation efforts. Ultimately, to ensure resiliency, to maximise efficiency, and to realise our decarbonisation objectives, we need to be considering an integrated energy system. Benefiting from hybridised technologies is what is essentially needed there. At this point, I'm going to hand over to Paul, who is going to discuss the approach to site energy at Sterling Pharma. Thank you.
Thank you, Adam. Very interesting presentation there. Good morning, everybody else. I was very recently asked to do a presentation alongside Clarke Energy and INEO at the Heat and Decentralised Energy conference about our shared project for combined heat and power. Let's see if we can. So I'll also talk not only about our combined heat and power facility, but also about Sterling's plans to optimize our energy use and ultimately reduce our carbon footprint. So who is Sterling Pharma Solutions? Sterling Pharma Solutions is a contract development and manufacture organization, CDMO, and we produce active pharmaceutical ingredients, APIs as they're called. These are the milligrams of active ingredients that you see mentioned on the side of your medication packages. The actual part of the tablet that's there to hopefully improve the patient, the end user's quality of life. Sterling have got a very strong pharmaceutical and engineering heritage dating back to the founding of the Sterling Drug API facility in the northeast of England in 1969. Now, the energy-intensive nature of pharmaceutical production has become a topic of concern over recent years within the industry as a whole. We're dealing with some very complex chemistries and multiple stage processes. These multiple stage processes can be very energy intensive. To put it in some kind of context, our site in the northeast of England has an average power demand of 3 megawatts and a peak demand of 3.6 megawatts, thereabouts, and a steam requirement of 8 metric tons an hour at 9 bar. Putting that into some kind of context, our current gas combustion on site is about 75% of our Scope 1 greenhouse gas emissions. So in 2018, Sterling set up a team to focus on site energy. Looked at various aspects to our site energy, starting obviously with primary energy costs and the predicted rise in energy costs. So looking at everything from the gas, the electric, the water, and then also on our delivered energy. So looking at things like our on-site transformers, steam generation and distribution systems, and our use of compressed air, the generation of compressed air, and of nitrogen and our water distribution systems. We've also started looking in depth at our point of use efficiencies. So obviously not just looking at how we get our utilities, but how we use them, how we maximize use. So we've been looking at all of our motors, pumps, fans, HVAC units, and even how we control all of those facilities. We've also started looking very seriously at our potential carbon dioxide reduction, starting off with a footprinting exercise just to find out exactly what we're starting with. And then ultimately, when we look at energy, we inevitably look at reliability of our energy supplies and where we use energy. So the two strategies work hand in hand, the reliability and the energy consumption. And as Adam alluded to before, a look at the site's resiliency. So looking at how the future changes in the country's network could potentially affect our own abilities to continue to produce. So when we looked at those lists of opportunities, one of the opportunities that stood out was that of combined heat and power, in particular the cogeneration aspect of electrical power generation and heat for us in the form of steam and also low temperature hot water. We looked at obviously all the options, and because our site is a 24/7 operation, 365 days a year. And because we have a good balance between our power requirements and our heat requirements, the CHP project really sort of blended nicely with our site profile. Also, with the particular CHP that we are looking at, with the hot water, the project has about 2,000 kilowatts of low temperature hot water available, which we can use all of that in our building heating systems. So the project's already underway with a handover date to Stirling of February 2021. And that includes all of the risks that we could foresee, so the Brexit risk that came with the project, and also the unforeseen risks that 2020's brought with it, the COVID pandemic. And really, at this stage, I would like to give some credit to everybody involved in the project, because the project remains on time and on budget, even with all of the various things that has been thrown at us in 2020. The slide now has a picture of the site that was chosen for our on-site high efficiency energy centre, which is quite poetic in that the site chosen was that of the redundant fuel oil storage system, and that's really been a good thing for Stirling. As you can see, the construction is well underway now. Move on. So I'll take you through some of the construction. So as I said, the ground was cleared of the redundant fuel oil storage. All the planning applications and environmental surveys went through the system. And we've gone through the difficulties associated with getting materials to site during lockdown, and have made good progress right through construction of the building itself, which is a fully insulated building, through to the installation of the equipment. So soundproof enclosure for the engine and the generator set, the large exhaust system you can see there in the background, which will take the heat to one of our high efficiency boilers. All of the boilers that have been specified as part of this project are high efficiency units. They're all fitted with modulating gas burners, modulating feed, and economizers. And also one of them has the ability to take the high temperature exhaust from the engine and use it to generate steam for the site. That's the alternator set going in, 16 tons of alternator going into the building. And the engine itself, as I said, the engine will also provide us with low temperature hot water, nearly 2,000 kilowatts of low temperature hot water for building heating. That's obviously something that we wouldn't get through just a procurement option of electricity. So CHP isn't the only thing that Stirling are looking at. One of the features that comes with the CHP facility that Clarke Energy are installing is a building management system and energy management system as part of the project. Now, this building management system is being cascaded throughout the site, and with the power management tool that comes with the system, it's a Siemens Desigo building management system. It can help us not only monitor the efficiencies of the system through monitoring the gas and the water going into the boilers and the steam being generated, and also the gas and the subsequent power being generated from the alternator set, but it can also help with smoothing out our peak demands. It can look at potential high energy items of equipment that are about to start, and it can back off other non-critical systems while those high energy systems start up. And that takes an amount of stress off the system. It also means that we can start looking at how we start neutralizing the effects of our peak demand profile. We've been looking also at our building utilization quite carefully, because we've got a lot of options on our site where, with a bit of thought, we can really look at how to reduce our carbon dioxide profile for the site. One of those is that we have quite a requirement for refrigerated storage and at the same time heated storage. So it makes sense really to grab that heat that we're stripping out of our refrigerated storages and put them into our temperature controlled heated storage areas. Hydrogen technology has been mentioned throughout the presentation, throughout this presentation and previous presentations. I was listening to some yesterday. One of those that's been mentioned is that of Northern Gas Network's Project H21. Similar to others, the ability to blend up to 20% hydrogen into the gas mixture. We looked at that at the very start of the project, and it was one of the things that attracted us to Clarke Energy and INEO, was their knowledge of the hydrogen blending of the H21 project, and the ability of the INEO Jenbacher gas engine to be able to take those blends of hydrogen all the way through to 100% composition of hydrogen, should we get there. The other things that we're looking at there is heat pump technology, which Adam mentioned. We've already embraced heat pump technology in our laboratory buildings and our development centre. We're seeing some great benefits from that. In fact, we're going to look at cascading that into our office areas next. Anaerobic digestion, now that's been mentioned as well throughout the conference. We have an £8.6 million project to install anaerobic digestion for treatment of our industrial waste streams. So that will generate a biomethane that we can inject directly back into the national gas grid. CHP, as I've said, it's already underway, and it's on track for handover in February. But it's also a good platform for initiating further savings, further energy monitoring and energy reduction projects. We've identified through this project about £250,000 worth of savings to our steam distribution and condensate return systems. Solar as well, it's another one that Adam mentioned in his presentation and others mentioned about, looking at a blended profile to energy use and energy generation. We've got a project where we're looking at about 3/4 of a megawatt of power generation just from utilising our roof space across site. And finally, the last project that we are currently looking at is that of tri-generation, which for a site like ours that has a high cooling demand as well as a heating demand, really sort of lends itself to a combined heat and power facility on site, because we can use that extra energy that's developed from the power generation in the form of heat. We can use that through absorption technology and adsorption technology to generate cooling for the site's production needs. I think to close, so it's important that all of these projects will benefit us financially. They will benefit us in terms of our carbon reduction, but there's a lot of other benefits that come with these projects, which are difficult to capture, difficult to measure, but they have an effect on site morale. They have an effect on people's mental well-being at work, that we're doing positive things. And have a positive effect with our relationship with customers and with our neighbours. And although these are difficult to quantify, they're worth bearing in mind if anybody else is looking at projects to improve their energy resilience and their energy use. So thank you. I'll hand back now to Adam so that he can hand on to Michael. Thank you.
Great stuff. Thank you very much for that, Paul, and a really interesting insight into the kind of ongoing activities at Sterling, and something that we're very proud of as a business to currently be proud of and grateful to being involved with at this stage. I'd like now to hand over to Michael Smeeth from INEO to give us an insight into how INEO are planning for the changes we've discussed, and I suppose an insight into the future for gas engines. Michael.
Wonderful. Thank you very much, Adam. And thank you very much, Paul, as well. It's always fascinating to see like the real life application of where our engines are going on site and doing something useful. As mentioned, my name is Michael Smeeth and I run the global resiliency business for INEO Jenbacher. The picture you see there is actually of our main headquarters and manufacturing facility in Jenbach, which is in the Alps. We're very imaginative about how we name our products, as all our Jenbachers are made in Jenbach and all our Walkershores are made in Walkershaw, Wisconsin. So if we ever add a third product to the portfolio, it's probably a pretty good guess how we'd name it. To give you a little bit of a snapshot of who we are as INEO, I just wanted to give a sort of like snapshot in numbers. We have around 64 gigawatts of generation delivered globally. And to put that in context, that's around 124 million European homes, or roughly 3 times the size of the power requirements for Germany. We have assets deployed in over 100 countries, and around the world, as well as going direct, we work with over 60 high quality channel partners, of which Clarke Energy is by far the largest, and I'm marginally biased here, but I would argue very much one of the best. In terms of the portfolio of engines, we go from about 200 kilowatts up to 10 megawatts in a single unit. And actually, our background is it's gas. I mean, we are built from the ground up for gas engines. We burn any type of gas. We're not a gasified diesel engine provider, so we're probably very much at the forefront of any form of specialist applications of gas. And I'll come on to that later because that's very important when it comes to hydrogen and the ability of our product to actually operate successfully on hydrogen. Now, to give you another little sense of this slide, this is also the compare and contrast to the rest of the world. This is normally what we show to an American audience. But to give you a sense, 64 gigawatts, well, there's 124 million homes in Europe. It's only 44 million American homes, or roughly 5 times the size of Texas. But that, based on the same numbers, gives you a bit of a compare and contrast just in terms of differing patterns of energy usage between the UK and the US, or Europe and the US. In terms of the sort of applications we'd use, obviously you've just heard very interesting story from Paul around an application of one of our engines being used for industrial manufacturing. But in terms of other areas we use, things like greenhouses. So again, we're the world leader in greenhouse applications, where the carbon dioxide from the exhaust gas is actually captured and reclaimed and used to actually effectively fertilize the crops growing in the greenhouse, as well as providing an even temperature environment. Independent power producers and utilities, the oil and gas industry, we use engines to drive compression, pumping, as well as for power generation. Something Adam alluded to as well was very much on grid firming. So we do an awful lot of work with grids around the world to make sure that if there's a dip in power or suddenly there isn't nearly enough renewables to come online, we have a fast frequency response and quick spin up engines that can make absolutely sure that the power keeps going. And right up to large industrial process manufacturing, so like steel, so hugely energy intensive industries, to make sure that they can keep the electrical and the heat load going when they need it, sort of thing. We do an awful lot in agriculture and food processing as well. So, a lot of food processing is incredibly energy intensive and has a huge requirement for electrical as well as heating energy. So we do a lot in that area to help take cost and carbon out, as well as provide a resilient infrastructure. We, contrary to popular belief, we actually probably do now increasingly more in the sphere of renewable energy, and not just in terms of burning renewable and green gases in our engines, but actually deploying integrated and hybrid solutions directly alongside renewable assets. Because of the variable nature of when renewable assets can produce energy, being able to have something alongside it that can provide stable baseline power is hugely useful. The other big sector, and actually again was mentioned, which was actually the growth of Clarke Energy in the UK, is around waste to power. So using things like landfill gas, so stuff that would have normally just been wasted, vented, flared, using it and actually turning it into meaningful and useful energy, which again has a huge financial benefit, but also has a huge benefit in terms of not wasting carbon. And finally, commercial and industrial buildings as well. Now, in terms of what we're trying to do, we as a company have always liked 3Ds, 5Es, 4Cs, so this is our 3Ds presentation. But the three core tenets of what we're trying to do, the first is decarbonisation. So using high efficiency, and I emphasise the high efficiency combined heat and power, one of the main aims is very much about using less carbon. All of the deployments that we would do with cogen and trigen would be very much aiming at making sure that we were lowering the carbon intensity of the pre-existing operation of that site, and in some cases incredibly significantly so, and I'll come on to mention a couple of real-world examples shortly. The other piece we're very big on is decentralisation of power. Historically what you had was very large centralised power stations which were single points of failure, where you had a large amount of transmission and distribution losses as you squirted power down the grid over long distances. Having distributed and delocalized generation means that you have on-site generation. It can be far more efficient. You don't have those transmission and distribution losses. And also, you no longer have one big single point of failure as well. So it adds very much to the resiliency of the power infrastructure. And finally, there is digitalization and big data. We fundamentally make large, heavy spinning equipment, but at the end of the day, that is stuff that turns off an awful lot of data. So we have been at the forefront of all the engine manufacturers that are actually going, how can we use this data to provide a better output and service to our customers? So we have many thousands of our engines globally are connected directly back to Jenbacher headquarters, undergoing analytics in terms of how is that engine running, what is it doing, how can it be doing it better? And the reason for this is not just to get good information on what's going, it also means that our customers, so people like Paul in the field, his engines will all be connected to my plant. And what can happen with that is it means that we can start predicting when a problem may occur and then prevent it from ever happening. So by looking at, tens of thousands of engines across the world, how they perform, we can spot trends that are happening and then go and nip in the bud. Now, this is also a part of our legacy heritage of having previously been part of General Electric. And this was technology that was very clearly developed as well for things like the aviation and aircraft engine area, because we wanted to make sure we could develop as far as possible a zero failure environment. It can never be absolutely zero, but we can get towards the stage where we have the most reliable product out there, which is incredibly important for you as customers. So Paul and his team need to know that they have reliable heat and power coming their way, because without it, their manufacturing process doesn't work, and that is their core reason for being. To give you a little sense of the history of us as an organisation, we started in the 1930s with our first engine, which was a Walkinshaw gas engine, and the first Jenbacher was created in 1957. But all through that, we've got a history of innovation. So at every stage, we were usually the first to do something, whether that was the first Lean-Ox lean burn engine, whether it was the first 20-cylinder and the first 24-cylinder engine. We were the first people to do a dual-stage turbocharged engine as well. And we hit a significant efficiency milestone this decade as well, where we basically got well over 50% electrical efficiency out of our Type 9 platform, which for an engine is excellent, considering the electrical efficiency of big combined cycle gas turbine plants. To be able to get that high out of a single engine locally is frankly game-changing. In terms of the Jenbacher product line, I won't go on too much about this, because for those of you who, unlike us, aren't massive engine heads, this is a picture of 5 green lumps of metal in front of you. But to give you a sense in varying sizes, the Type 2 is the smallest engine, and reading up to the Type 9, which is the one there in the top left. They all have different operating characteristics, and they also have, some of them have overlapping power profiles. This is because depending on your application and your need, it's not as simple as a 1 megawatt engine does the same for everyone. So it might be that we have a different platform that absolutely ekes out the best efficiency for the sort of situation you're in. And also, unlike some people, you don't buy these off the shelf. When you order an engine from us with a partner like Clarke Energy, the exact situation it's going into is analysed, and then the best possible engine is created for you, right down to going, what do the top of the piston heads look like? How are the cylinders redefined? And because of doing that per job, it actually means that what you're getting will deliver absolutely the highest possible efficiency. To give you some real world examples of where this works, one company that we think you've all known is Coca-Cola, one of the world's biggest brands. And we've worked with Coca-Cola extensively all over the world. The picture you see there is one of Coca-Cola Hellenic bottlers' plants in Romania. Now they have two J620 engines with supplying a total base load of 6 megawatts of power. And that's a very impressive, super high efficiency plant that means that Coca-Cola can manufacture their product and bottle it with Hellenic, with their biggest European bottling operation, efficiently. The other thing that people don't know about as much is we also, with Hellenic bottlers and Coca-Cola, have a very large plant in Northern Ireland, so slightly closer to home for those of you based in the UK. And actually, that's a very innovative quad generation plant. So I know you in Paul's presentation, tri-generation was mentioned. We do also do quad generation. So there'll be electrical generation, there's heating, there's cooling, and then the quad is the reclamation of the carbon dioxide from the exhaust. So the Hellenic bottling plant in Northern Ireland actually reclaims the carbon dioxide from the exhaust of the engine, scrubs it to turn it into food grade carbon dioxide, and then it's used to carbonate the bottles of Coca-Cola you drink in many European countries. So again, it was another way of providing an innovative solution to a customer that also lowered carbon, and it gave them the ability to be self-sufficient in terms of being able to supply CO2 for their beverages. And when there was a worldwide shortage of CO2 recently, it actually meant that they were able to keep producing more effectively than some of their competitors. Now, I was emphasizing earlier how all our engines are green. They're not all green. This one is very, very electric pink. I mean, trademark, almost bright Barbie pink. This is actually in a large hospital in London, in St. Bart's Hospital, in fact, the oldest hospital in England. I think it was founded in the 1600s. Now, what was interesting with this is not just that it was a very high efficiency installation of an engine that's providing tri-generation and that it's, saving 1,500 tons of carbon a year, which, to give you a sense, that's about 750 cars off the road. But actually, that was more importantly a quarter of the carbon emissions for that site. It means that they've got 24/7 baseline power. And as a hospital, that's incredibly important. It means if there's a brownout in the local grid, they keep running. And actually, they're able to keep operating all those critical hospital infrastructure systems. This is something us and Clarke Energy do in more hospitals than pretty much anyone else in the country, and it's a great application. The reason this is exciting, though, is two reasons. The reason it's pink is that all the money that was saved from this engine in cost every year, the hospital trust has reinvested into cancer care. So we're very proud as Clarke Energy and Nineo to be able to say that this engine has saved lives, because actually it has freed up hundreds of thousands of pounds that have now been directly invested back into clinical services. And I think we'd all agree that actually I'd rather the NHS was spending money on treating patients than buying electricity. So for us, that's one of the reasons we did this. Also, it was very innovative as well because it was designed to a full turnkey energy performance contract that sat inside a PFI hospital agreement. So we were able to go to a hospital and say to them, for no upfront money, no capital required, we will come and do this for you. It will pay for itself out of its savings. It will return money to the hospital and it will save carbon. And we were able to deliver that successfully. And I think it's the first time that's ever been done in the UK to insert an active EPC into a PFI agreement. So we're all incredibly proud of it. And actually in the first year of operation, that site actually massively outperformed what it was predicted to do. So it managed to return even more money to the hospital and save a higher amount of carbon, which is excellent. And that's a single engine scale. To give you another more municipality scale, this is a flagship project with our Type 9 engine. In fact, there's 20 of them in there, providing nearly 200 megawatts of power, which is almost previously unheard of from engines. That was kind of in turbine territory beforehand. So one of the reasons we wanted to do this was to prove that super high efficiency quick response engines like our Type 9 were able to provide power at this scale, 200 megawatts, and also efficiently and cost effectively. So this at Stadtwerke, which is basically the municipality of Kiel, which is a big city in Germany, this is the largest ever plant of its size, a type delivered in Germany. But to give you a sense, it's reduced the carbon emissions for that Stadtwerke from the previous plant, which was 1.8 million tons, down to 540,000 tons. So if you want to step back and think about that, that is nearly 1.3 million tons of CO2 that have been abated by using high efficiency Jenbacher engines as opposed to what they had in place before. The other thing that gives them is much more flexibility in terms of quick response and being able to spin up different levels of power block. So if they need to run the plant at half load, it's immeasurably more efficient than it would have been with their previous thing. So for us, we are very proud of the fact that we've been able to push the envelope and deliver something very new, different, and actually what we think is the future. Talking of the future, one thing we want to talk about was hydrogen. Now, hydrogen, I'm sure for all of you who've been attending a wide range of the sessions in this great couple of days, has been talked about an awful lot by people. Here is the difference with hydrogen and us compared to some people else is we've been working with hydrogen for a long period of time, and we actually have stuff on the ground running and operating today. So Hachiko in Argentina is a hydrogen hybrid test site for us, where actually on site there are electrolyzers producing hydrogen. We have Jenbacher genset on the ground as well, and we've been there experimenting with various different types of blending of hydrogen into natural gas to actually see what effect it does, to make sure that it works with the technology. As mentioned previously by Paul, there's been a lot of work looking at fuel injection of hydrogen into the natural gas network. Now, not all engines are built equally, and not all engines can handle the same flow of hydrogen coming into them. We're very proud that INEO Jenbacher engines can, and actually we will happily promote our engines as being hydrogen ready, as, to be honest, today we know they are very comfortable running on a mix of up to 20% of hydrogen, which I think people have said is the maximum people are willing to inject. Ours will go beyond that, and in fact we have engine platforms running happily on 100% hydrogen. They have to be set up to do that, but we're already doing that around the world. The one thing I would say about hydrogen, this is an interesting one from that Hachiko site in Argentina, is that depending on how much hydrogen you actually mix in with the natural gas, after a certain percentage, you'll see quite a significant quick drop off in the power output. So if you look at that graph there, up to about 26, 27% hydrogen mixing, that's fine. As soon as you go above that, you start seeing quite a quick decline in the overall power output. You see a significant derating. Now that's interesting because that's actually us looking at a typical 420 engine. That isn't an engine that was modified specifically to be a hydrogen engine. So that's actually direct gas injection into a normal genset, where we would actually just look at software changes as opposed to hardware changes, maybe a few other little tweaks. But I just wanted to point this out to people that actually, depending on the fuel that goes in, has a huge influence on the power load that comes out. It's not just as simple as switching to hydrogen tomorrow. In terms of where do we sit in a renewable and hydrogen world, I think the honest answer is we sit at most points of this. So whether that is making sure that we are helping to decarbonize at the moment, so we can actually get towards zero carbon in 2050 by taking significant carbon load out of existing infrastructure, whether that's working with biogas and biofuels and green generated fuels to produce energy from those, whether that's working directly alongside renewables to provide fast spinning pieces, or whether that is actually just looking at other synthetic fuels, or looking at things like ammonia, looking at synthetic methane, ethane, looking at methanol. The fact is, we see a very bright future for our engines, particularly within the mix of helping deliver a very strong, resilient and carbon-free infrastructure within the UK. And I think, it's very rare now that, particularly in the UK, when we're talking to a customer, that one of the things they're not thinking about is their carbon intensity and their footprint. And, when we're doing a good quality CHP or cogen or trigen, I can't think of a single installation where we wouldn't be saving significant carbon. And actually, even with a very conservative suggestion of decarbonisation of the gas grid, we will still be overwhelmingly decarbonising well into the 2030s. So when people sometimes worry a bit about going, is this yesterday's technology? We say, no, it's absolutely not. We have a history of innovation. We're still innovating. And actually, to that end, what you will see with hydrogen is essentially one of three approaches here. So one is an engine where you just see hydrogen is injected in the natural gas pipeline. We're ready for that. That is now, basically. We're ready to roll with that as long as we know the percentage of hydrogen that's in there. We can burn it. We can adjust the engine to keep the exact same high level of efficiency. And in fact, all the stuff that we've developed over the years in terms of being able to tweak our systems perfectly to make sure it's absolutely maximizing the gas coming in applies just as well to hydrogen, which has given us, to be honest, quite a competitive advantage over other people. Following that, there's the local mixing of hydrogen. This is more complicated. So this is where on site you may have normal natural gas coming in and you are mixing hydrogen yourself into that, and then it's going into the engine. We have a slightly different engine platform and optimization for that, but again, we're very happy to be able to accommodate that. And, in partnership with Clarke Energy, we will happily look at installing those solutions to meet your needs. It's a little more complicated, but also then does have some other slight benefits that it lets you do this more quickly. Until there is a hydrogen injection to natural gas pipeline, it means overnight you could actually be using a percentage of hydrogen to lower your carbon impact. And finally, option C there is actually a pure hydrogen engine. And there are clearly applications for this. We've seen some very exciting announcements in the news over the last couple of days from people like Airbus around releasing entirely hydrogen-based aviation fleets and their projection for those. And again, this is our version of that. So, when that hydrogen is ready to go, we are more than ready to go with engines that will just deliver that zero carbon energy, heat, cooling for you. So in summary, one thing to remember, depending on how much is in there or it's blending, it changes the gas attribute significantly. When you're looking at what you do, make sure your existing hardware and plant is able to cope with it. We're very proud that ours can, not everybody's can. And the last thing you need to do is do something for the right reasons, namely to decarbonize, and find that what it does is cause a catastrophic failure of your wider plant and machinery, because that will undoubtedly have not just a huge financial impact, but a huge environmental impact on you as an organization, and very much be the opposite of resiliency. Within certain limits, controlled hydrogen blending we think has a huge role, but we see that on a case-by-case basis, but we would work with you on that. But the good thing is it also reduces knocking it's bad, but it reduces the knocking resistance. You're more likely to get pre-ignition, to get pinking, so it has its downsides. Uncontrolled hydrogen or variable quality hydrogen is an issue. One of the problems that we've seen on some of our engines, particularly when we're working out in the oil and gas field, is when you're getting unpredictable quality fuel coming in and there's a large swing. Now, we're very good at coping with that, but it does have its downsides as well. So it's important that we know what's coming in. And again, I think, to be honest, there's no one better than Clarke Energy that you could be working with on looking at your particular, for instance, of that, as they are very squarely the market leaders when you're looking at non-natural gases and combustion in this country. Very interested in talking to you about conversion of your existing engines. But one of the things we're also very interested in talking to you about as well is us and Clarke Energy are very happy to talk to you about, even if you already have something in sight, we're happy to look at coming in and putting something entirely new and different and better in for you, and doing it in a way where it can be fully financed and still guarantee you savings. So, I will be quiet now because I'm going to start getting a bombardment of text messages from our moderators telling me to please shut up and be quiet so people can actually ask questions. Can't really blame them for that. So I hope you've enjoyed listening to us. And again, I just wanted to thank Adam and Paul as well for their great talk, and actually just move on to I'll hand over to Adam, but just move on to the final piece and say thank you for listening, and we hope you have questions. And also, I would also just say as well, please do use the Whovier app. If you have any other questions and bits, you can contact all of us directly. We're all on there. We're also all on LinkedIn. So if there's any other questions, issues, concerns, or you'd just like a chat, drop us a note, and we're super happy to talk to you. Thanks very much for listening. Adam.
Thank you, Michael. So I guess as a quick summary and an introduction then into the question and answer session, I think there's a couple of salient points that both Michael and Paul have raised, which I'd like to just reiterate, if I may. So as Michael has said, meaningful use of resources is critical. Flexibility to respond to ever-changing conditions is evidently then a benefit that INEO and Jenbacher can bring. And I think an interesting insight from Paul was that both quantitative and qualitative benefits of the energy systems discussed have an impact in that decision-making process, and the socio and economic kind of impacts and considerations need to also be thought about in the context of analysing your future energy system aspirations. So natural gas then, it may be a carbon emitting fuel, but rather I think it should still be considered as a transitional fuel, driven by efficient use and as a means to enable renewables investment on that path to zero. Beyond that, increased decarbonisation of our gas systems, I think, can help secure the future of highly efficient on-site generation to support our customers' needs. And couple that with delivery of an integrated energy solution comprising hybridized technologies, I think is hopefully the future that we will achieve, that will help us rather achieve net zero carbon with reduced energy costs, which kind of quite nicely brings us back to the title of the session. I'd like to open the floor to questions. Please do use the Hover app. I'm still not entirely sure how I'm supposed to pronounce that, but never mind. I can see from our moderators that we have a few questions that have already crept in. So I will read a selection of these out and invite both comments from Paul and Michael as appropriate. And as Michael has suggested, if there are other pressing queries, please do reach out to us through the app, through LinkedIn. You have our contact details, I think, at this point. So, starting then, is it feasible to install CHP now, considering future hydrogen networks? I hope that was kind of discussed or at least highlighted within the presentation, but the answer is yes. And certainly from our perspective, utilizing the considerable economic benefit that CHP still brings, I think should be seen as a methodology for driving renewables investment down the line, but also driving efficient network infrastructure, incorporating hydrogen in the future. I don't know, Paul or Michael, would either of you have anything that you'd like to add to that?
Yeah, just a bit. Look, 100% agree. It is very feasible, but I think it's a really
Michael, I'm afraid you're on mute.
Oh. I thought I'd unmuted. Oh, sorry. Well, look, I think it's a really important point to make, actually, because some people are getting nervous about putting new infrastructure in that burns gas because they go, well, gas is not a carbon negative fuel. I think the really important thing to remember here is that it's about doing as much as you can now on the journey to carbon zero. And what worries me is sometimes people postpone doing something now that could have a significant impact on their carbon load today, as well as enabling the transition to zero carbon. I think, yes, go do CHP. And actually, when it's 100% hydrogen, you'll still be doing CHP. The reason that gas is bad at the moment is it's because it's not a decarbonized fuel source. As soon as it becomes a decarbonized fuel source, it becomes even more efficient and carbon free. And we already have a great distribution infrastructure in the UK. So I would say don't put off, but whoever you're doing CHP with, ask the question, what are your plans for the future? How does this fit in? Will you guarantee me that actually we're able to be carbon lowering throughout the life of my project? These are the sorts of questions you need to ask because actually they're important to you. And we're happy for you to ask them because we know we can answer yes to them. And I don't think everyone can, but broadly, that's a very long way of saying yes, it is.
If I can join in as well, then I'd definitely agree with that it's well worthwhile doing. Sterling's commitment to reducing carbon, we've got a signed agreement to reduce our carbon by 50% by 2025, which isn't very far away. And the CHP forms a big part of that. It does reduce our carbon footprint quite significantly because of the on-site combustion that we require anyway to generate steam. To do that through first generating power and then using that exhaust gas, which is coming off at, I believe, between sort of 300-400 degrees C, using that to generate the steam that we require anyway, it makes perfect sense to get the most out of the energy that's in the gas. So definitely CHP is well worthwhile.
Thank you, which brings us on quite nicely, I think, to a couple of questions that were somewhat geared towards yourself, Paul, but I think there's clearly future additional considerations, I think, that Michael and I perhaps can bring. So one of those things, does anyone have tangible examples where projects have delivered those wider socio-economic type benefits that you discussed, Paul?
Well, certainly more and more we are being asked by our customers what our approach to energy is. As more people get asked to report on their their carbon footprinting, whether it's a scope 1, 2, or 3 with their carbon, then ultimately people are interested in every aspect of that supply chain, and we are a part of that supply chain. So we need to do something positive and proactive about reducing our amount of carbon.
Perfect. Michael, I think there's probably a couple of examples, certainly within the health service in the UK, where the wider benefit of CHP can be discussed.
No, well, very much. I mean, if you talk about, say, let's take a big London hospital trust like Guy's and St Thomas's Hospital. You know, they are huge teaching trusts in the middle of London. One's just by the Houses of Parliament, opposite the water, and one's just by London Bridge Station. You know, we have a 3 megawatt engine operating in each site there. And I think that saves that trust around £2.5 million a year. Roughly speaking, those are their own figures. But more importantly, it's many tens of thousands of tons of CO2 that are saved. So in fact, actually, when we did that installation with them, they went from overnight being one of the most polluting trusts in London to being the least polluting overall because of the huge impact that made. What it's also done is allowed them to more creatively deliver their services. So they've made sure that they've actually had meaningful use for all the heat that comes off that engine. So much so they actually now run a sterilisation service for all the medical instruments for most of the hospitals in London because they had an extra steam load. But actually the biggest thing for them wasn't actually just the cost out and the carbon out. It was the fact that they are now comfortable that if there is a power interruption or an episode, they can keep running. So actually I had this benefit that they've kind of got all together. And you know, they want to be a good corporate citizen. You know, London has some of the worst air quality in Europe. So anything where they can actually be lower emitters and more sensible uses of energy, it works incredibly well. And actually, off the piece of work we did with Bart's Health for the large pink engine we showed you there, we actually, in combination with the FM provider on site, Skanska, funded a project around changing behaviour. And actually, we use the engine as a catalyst of change for behaviour to get people thinking about the environment. And we managed to see a significant uptick in patient satisfaction and also more people actually engaging with their environments. The other thing I'd say is think about some of the intangible benefits that comes from these. Is, you know, for me, like I say, my job title has resiliency in it, because for us, to anyone we work with, resiliency means not just financially resilient, it needs to save you money or it just needs to save you carbon. It also needs to actually make your organization more resilient as well. And whether that means it's keeping the power on to keep you going, whether it means that you're actually being able to use it as a tool to engage with your workforce and your customers so they can understand that your goals and objectives are shared with them. So particularly if you're in a direct-to-consumer business, say you're a food manufacturer or something like that, being able to understand and work with your consumers to understand that your production of chocolate bar X, drink Y, meal Z actually is now less carbon intensive, and you care about how you're doing these things, also has a value in there too. So I think, you know, it's, and we don't put a value on that. We don't try and sell you that, but it's something you need to think about as well, because it does intrinsically have a value to you in terms of actually how you market and sell your products.
Brilliant, thank you. And a few more questions coming in around similar themes and exploring these kind of continued themes. So, for example, can we really achieve net zero carbon using gas? And a similar question that kind of links in is, what is the role of hydrogen and biomethane in decarbonising the grid? How does this then fit with CHP? And again, I hope that these are questions that were answered to an extent throughout the presentations, but you know, I'm happy to explore those concepts a little bit further and invite Paul and Michael for their comments.
Well, look, and I'd just say on that, is it everyone installing CHP tomorrow as is the silver bullet to getting us to zero carbon by 2050? No, it absolutely isn't. Is it a core thing that we should be doing to help us do something that's going to be very difficult and seismic change in terms of how we provide power? It absolutely is. And I think my worry is that you've got policymakers with incredibly good intentions at the moment, wanting to actually work out how we can achieve zero by 2050. It's an aggressive and ambitious target. And actually kudos to the UK government for actually legislating for that. That's ahead of an awful lot of their counterparts in terms of what they've done. But I think it's also important that don't let, you know, perfection be the enemy of good. We have actually seen, and we've had a lot of conversations with some people who have been worried about doing something because it doesn't get them to zero tomorrow. So by doing nothing, it's almost impossible they're ever going to get there. And actually, in the meantime, they could be saving a lot of carbon and a lot of money and having more resilient infrastructure. We don't know what 2050 is going to look like. No one in the industry knows exactly what is going to happen by then. All we can do is guess and look at what may or may not happen. What I can tell you, though, is that as a company, we are innovative and respond to the situations to make sure that we can actually provide the best solution with the technology available and help develop that technology. Just as we've done with hydrogen. As hydrogen's come to prominence, we can run 100% on hydrogen, fine, right? So the fact is, make sure that you are picking a partner that actually has that kind of ethos and that actually will get there. You don't really want someone who's just selling you a lump of metal, taking their money and leaving. You basically want to see this a little bit like a marriage, because actually once we've come in and done something for you, you're with us for a while, because, you know, maintaining it, running it, making sure it works, those are incredibly important things. And make sure that you're working with a partner that you truly believe is actually there for the long run and will actually help you meet your objectives of hitting zero carbon. And, you know, I'm not saying it's just us who can do that. I would say, obviously, because I'm biased, we'd be the best at it. But do think about that. So I'd say, look, you're going to have worries. You're going to be interested about how this may or may not work. What I would say is have a conversation. Ask difficult questions of the people who are making you promises. And if the people that are talking to you about doing this can't answer those questions satisfactorily, ask more questions and ask other people questions. We always welcome you asking us questions. You know, if any one of you wants to pick up the phone to us and talk to us what we can and can't do with you, we'll be straightforward, we'll be honest, and we'll give you a true version of it. We will never overpromise and underdeliver. I mean, that's one of the things that I love working with Clarke Energy about, is that they're mind-numbingly bloody conservative sometimes in what they offer, but they always overperform. And for me, look, that's brilliant. You'd much rather have that than someone who's promising you the earth and delivering nothing. So I'll finish with my advert there, but do think about that.
Yeah, and I think it's an important consideration as well when we're considering the role of gas and the role of CHP. You know, looking towards the future, we're not only seeing a transitional phase with regards to kind of energy generation and an efficient use of generation in a baseload respect, but also for backup generation, backup infrastructure at data centers, hospitals, banks, etc. We're starting to see that change in philosophy and recognition, really, that the traditional means of backup generation, which invariably was a diesel generator, actually is not necessarily the most efficient or least carbon emitting option in that respect as well. And utilizing, you know, an existing storage mechanism, i.e. the gas network, the infrastructure that is pre-existing, and replacing some of that aged, inefficient backup infrastructure with modern, high efficiency, fast start gas alternatives is actually another interesting proposition, again on that transitional path, as it were. And there's been an interesting question around energy density of hydrogen, and a kind of an acknowledgement that this is approximately maybe a third of that of natural gas. So does 100% hydrogen ultimately mean a third of the power rating of a unit? As Michael showed with the example of Argentina there, up to a point we can, with blended fuel, we can maintain full output on the engines. But there does become a point at which you will start to see a power reduction in a natural gas optimized version of the engine, because you have absolutely a lower calorific value fuel. And as that continues to increase in blend, you are likely to see an increased level of output reduction, unless you can push more fuel into that engine to compensate for the reduction in calorific value. The problem therein becomes actually how can I physically push that much fuel into a predefined gas train and gas intake. So we need to be considerate of the fact that yes, there could ultimately be a reduction in power if you have a natural gas optimized engine taking increased levels of hydrogen, maybe 20 or 30 years down the line. But importantly, 20 or 30 years down the line, INEO will have continued their research and development into combustion of hydrogen and optimize those solutions to minimize that potential differential. And you know, if we consider that it's going to be a long, long time before we ever see a 100% hydrogen network, I think. So there's likely to be some changes. Increased levels of biomethane will continue to maintain higher levels of calorific value. Increased levels of hydrogen will then reduce it. And it's all about optimization, which I think I refer to in regards to routine maintenance activities. If it looks like the way that we designed the engine 7 years ago is now not how it's going to operate 7 years from now, then let's make a change to that unit in the field during routine maintenance.
Look, and actually that's an incredibly important point that Adam raises there, that when you stick an installation in, it's not set in aspic, it's not that's how it's going to run till the end of its life. We are constantly evolving through software as well as hardware tweaks, how our engines and our products run as basically things change. And what you find is, like all engines, that eventually they'll come to a major overhaul. And actually we will look at we can do significant upgrades at those points where you've almost effectively got a brand new engine type going in. So, we've got clients that in the UK we've worked with Clarke Energy for, 30 years, where they've had an engine running, but it's not been the same engine. There's been significant upgrades, improvements, and various other stuff. So, what they did at the start of their life is now very different to what they're doing now. But the one thing that's been true all the way through is they've had literally the best in high efficiency CHP they could have at that moment in time as you went through. And this is the other thing I would say to people, not to worry too much about making a commitment to do something like this, is that actually you just need a commitment from whoever's doing this with you that it will be running at the best it can possibly be running at that current moment in time, but it will keep going. What you don't want is a commitment to going, it'll do this today and we're never talking to you again. That is the last thing you need. What you want is people to be able to say, this is our path to us helping you get to zero carbon. And actually it's not just going to be about us, it'll be about multiple technological interventions. As Paul mentioned earlier, they're looking at a whole range of things that they can do. And actually the Clarke Energy team past masters at integrating multiple technologies around one of our engine gensets to be able to actually deliver this. And so I think, it's a conversation, but the technology is constantly evolving, but so are we.
Yeah, if I can join in with that one there. I think it's important to note that energy generation isn't Sterling's core business. So we very much needed to partner with somebody that where that is their core business. And when we've looked at our energy center, the one that was on all the photographs, everything in there is pretty much modular, and items can come and go as things change. So we're aware that that whole engine can come out of our facility and go away and be either overhauled or replaced entirely. So it is an important part of anybody's project if they're looking at it, as you say, to partner with the right organizations that can look beyond the exact physical items that are on the table at the moment. So definitely I would agree with Michael and Adam on that who you partner with is very important.
Thank you. We have a few minutes left, or up to 10 minutes left, I believe, if we need to go all the way. If you do have any more questions, I implore you to utilize the Q&A, a session Q&A panel through the app. Please do. I can see that we still have a reasonable audience at this time. You've not all left us yet, so thank you for that. An interesting question that was raised by Matthew Barnett is how will carbon capture and storage impact the cost of hydrogen production from fossil fuels? Will it then be comparable in cost to electrolysis? My thanks to Stefan Cook, who's posed an answer to this question within the app. And actually, this is quite good testament to the way that this digital session is being held. And the live interactions between people I find quite interesting. And I'll just kind of explore Stefan's response or dictate Stefan's response in that respect. So carbon capture and electrolysis are kind of competitors. If CCS becomes economical, then hydrogen production by electrolysis is not really needed anymore. If electrolyzers go through the economies of scale first, then there is no real need for hydrogen CCS. So it's an interesting insight that whilst current government kind of rhetoric, not policy but rhetoric, would suggest that, you know, to do one you need the other, and then unlocking that hydrogen supply chain can't really be achieved without carbon capture or CCUS. You know, it's interesting that they can almost be considered as competitors, and if one happens at scale first, it negates the potential impact of the other. And I don't know, Michael or Paul, whether either of you have any feelings on carbon capture and electrolysis and kind of the overall hydrogen supply chain.
I was going to say, I think like a lot of these things, I don't think it's going to be all one or all the other. I mean, the economic and efficacy factors you mentioned are going to play a huge role, but also just in terms of the practical infrastructure that's there. So if you think you may have a huge amount of renewable generation in an area without necessarily the grid infrastructure to port that power elsewhere, and also its variability, suddenly hydrolysis effectively means you can have a very good virtual chemical battery storage of hydrogen, which is easier to transport to somewhere else, which, you know, is a very different potential then. So I think what you will find is, because of the fact that these things are rarely simple and black and white, and it depends an awful lot on topography, geography, other issues, grids, infrastructure, cost of delivering more grid infrastructure, you're going to see a mix. I think the fundamental economics of basic and efficiency of hydrolyzers versus the same for CCS is going to play a big role in that, but it's not going to be the only role, because there'll be times when actually one is just not going to cut it in terms of what you're trying to deliver because of the other factors around. But actually what it might well then do is influence what infrastructure you build around which technology, depending on its price. But I think it's going to be a movable feast, and I think, you know, I think I'd be surprised if we saw all of just one and not just the other. You know, one may well win out in terms of overall prevalence, but I'd be very surprised if one entirely disappeared. Look at that, I've stunned Adam into silence. That never happened.
Never. Yeah, thank you. And an interesting comment that's been made again, and this is fascinating actually seeing this Q&A kind of develop live, and an interesting comment by Mark. You know, presumably the oil and gas suppliers are going to push hard for CCS in order to kind of maintain their relevance in the future, and ensure that people are still consuming natural gas on the system, which absolutely I think is the case. But interestingly, you are seeing increased drive from the major oil and gas suppliers into decarbonisation methodology. So yes, CCS is one of the considerations, but as Michael says, ultimately we're likely to see a wider mix of technologies being deployed as suitable throughout various parts of the system.
Well, and I think, and on that as well, you're quite right. I mean, large oil companies are fundamentally businesses. So yes, they will try and promote and protect their interests, but they also understand the way the wind is blowing, not to use too much of a pun, and will invest in other technologies there. I think it was interesting that one of the oil producing states has heavily started divesting its investment from oil into renewable technologies, with the exact comment, which I particularly love, is the Stone Age didn't end because they ran out of stone. Right, and I think that's actually the same issue with the oil age. The oil age isn't going to end because there's not necessarily any oil left. It's going to be for different reasons, and actually you've got to understand the way these things are going. All we have to see at the moment is basically, like yesterday there was a conference held under the C40 Global Cities banner, where many cities, major cities headed by the mayors of New York and London, have all signed divestment pledges from investing in any assets that are carbon assets, oil and gas, right? People, and they understand that's hitting them, and they understand that they basically want to keep relevant. I think only today or yesterday, Microsoft and Shell have just signed a development partnership around technology to look at decarbonisation in the future. This is what's happening. This is the reality of business, and it will get there. And I think this is why I think that, you know, we need to really shy away from seeing these things as these guys are all good, these guys are all bad, or this technology is all good, this technology is all bad. The reality is there isn't one thing that is perfect at the moment. It's going to be an interesting mix of services and approaches and technologies that deliver what we want. And actually that mix won't have a universality globally either. There'll be stuff that suits particular geographies better than others, just by the very nature of where they are. So I think, I mean, actually, you know, as someone who fundamentally works in energy, I think it's an incredibly exciting time. You know, we are on the cusp of huge evolution and change. And with the announcement of China a couple of days ago actually pledging to be carbon neutral by 2060, which still isn't soon enough, but frankly an amazing piece for the Chinese government to actually come out with, means that, you know, the weight of momentum is in the world. And so all the people who might have tried to stop this before, I think, have grudgingly accepted that it is going to happen, and they've realised there's money to be made in making it happen. So, you know, I'm actually quite hopeful that we will get more and better and innovative stuff. But I think, you know, for those of us, and I'm sure for most of you listening to this, it's going to be interesting times.
Great stuff, thank you. I think that's covered most of the questions that we've received, not all, albeit not all, and I'm aware not all. But I would probably like to take a few of them offline in any case, and so I'll message a couple of you guys that have presented interesting questions separately to the kind of the live session, if I may. So finally, I'd like to say thanks for your attention. And I hope you have found today's session informative and beneficial. It's certainly been an interesting discussion, and I extend my thanks also to both Paul and to Michael for their insight this morning. And hopefully, you know, hope that everyone enjoys the remainder of AD Heat 2020. Thank you very much. Cheers, guys.
Okay, so thanks very much, everyone. Thanks, Adam.
Thank you. Thanks.